Welcome to this calm journey into the world of organic chemistry. As you settle into a restful state, allow your mind to soften and your breathing to slow down. This experience has been designed not to overwhelm you, but to gently guide you through a structured lecture that works both as a source of knowledge and as a relaxing background for sleep. Whether you are a student preparing for exams, a lifelong learner exploring new fields of science, or someone simply seeking a soothing way to fall asleep, you are in the right place. Think of this session as a blend of relaxation and education, where the rhythm of words and the steady flow of concepts help your mind drift into both understanding and calmness. Organic chemistry is often called the chemistry of life. Every living being, from the smallest microbe to the most complex human body, is composed of molecules built upon carbon. When we hear the phrase organic chemistry, it might bring back memories of dense textbooks, laboratory experiments, or complicated reaction mechanisms. Yet, beneath the surface, organic chemistry tells a simple and profound story, the story of how atoms come together to form the substances that make up life and the world around us. This lecture will unfold that story at an unhurried pace, so that even as you listen in a state of relaxation, your mind will gradually absorb key ideas, patterns, and relationships. The practice of sleep learning is not new. People have long wondered whether the mind, in its resting state, can continue to process and internalize information. While deep, dreamless sleep may not allow for conscious learning, the state of drifting, the borderlands between wakefulness and slumber, often leaves the brain open to gentle suggestion, memory reinforcement, and pattern recognition. By hearing calm explanations, repeated structures, and familiar contrasts, the listener's mind begins to form quiet associations. When combined with the inherently patterned logic of chemistry, this makes sleep learning an effective way to gently reinforce knowledge. In this introduction, the intention is not to rush toward complicated formulas or intimidating diagrams. Instead, the goal is to set a peaceful foundation, preparing you for a slow unfolding of the subject. Think of this as an invitation to a long voyage. Imagine sitting by the shore of a calm ocean at night. The waves roll in and out in steady rhythm, never hurried, never forceful. This is how the lecture will move, one idea flowing into the next, each connected, each building gently upon the last, with no pressure to memorize or solve, only an invitation to listen and relax. Organic chemistry can sometimes feel like a dense forest, filled with countless trees and branching pathways. At first, it may seem impossible to find your way. But when approached with patience, that forest becomes a peaceful sanctuary. The trees become familiar, the paths reveal patterns, and what seemed overwhelming at first becomes a structured and calming landscape. The purpose of this lecture is to serve as a quiet guide through that forest, pointing out landmarks, showing recurring shapes, and making the journey feel less like a struggle and more like a meditation. As you listen, you may notice the rhythm of contrasts. These will become guiding anchors: life versus non-life, simple molecules versus complex structures, stability versus reactivity, symmetry versus asymmetry. Contrasts help the mind learn because they give it clear reference points. Just as night is understood in relation to day, or silence is noticed against sound, so too chemical ideas become clearer when compared against their opposites. This method of framing will appear again and again, not to add difficulty, but to allow gentle reinforcement through balance. It is also worth remembering that organic chemistry is not confined to the laboratory. It is in the food we eat, the medicines that heal us, the fabrics we wear, and the fuels that drive our world. Even as you drift toward sleep, think of how much closer this subject is to your everyday life than you might have assumed. The apple on the table, the fragrance of a flower, the warmth of wood in a fire, all of these experiences arise from the interactions of organic molecules. By linking the subject to ordinary life, the lecture becomes not only an academic exercise but also a meditation on the connections between science and experience. As this introduction draws to a close, let the calmness of the moment sink deeper. Your breathing remains steady, your body feels at rest, and your mind is ready to float along the current of knowledge without strain. The next sections will gradually move into the building blocks of organic chemistry, starting with the history of how it came to be and the fundamental principles of atoms and bonds. For now, simply carry with you the reassurance that this is a space for gentle learning, not hurried memorization. The journey ahead is long but smooth, designed to nourish both curiosity and restfulness. Let go of any tension, trust the rhythm of the words, and allow the gateway into organic chemistry to open softly before you. Organic chemistry did not emerge all at once as a complete science. Its roots reach back to the earliest days of human curiosity, when people tried to understand the substances that surrounded them in daily life. Long before laboratories and microscopes, humans encountered organic compounds in the form of plants, oils, resins, and medicines drawn from nature. These early discoveries were not explained in terms of atoms or molecular structures, but through experience, trial, and a mixture of observation and imagination. The idea of a special life force, something beyond ordinary matter, shaped early thinking about organic substances. It was believed that the products of living things could not be created from non-living matter, that something unique animated them. This belief is often called vitalism, and it remained a guiding assumption for centuries. Understanding how this early belief gave way to modern science helps us see not only the foundations of organic chemistry but also the progression of human thought itself. In the 17th and 18th centuries, alchemy began to evolve into modern chemistry. Alchemists were fascinated by transformation, searching for ways to purify metals, to create medicines, and even to produce the legendary philosopher's stone. They worked with distillations, extractions, and reactions, though without the theoretical framework we have today. Slowly, their empirical results laid the groundwork for systematic experimentation. By the late 18th century, chemists such as Antoine Lavoisier introduced the language of elements, conservation of mass, and quantitative measurements, giving structure to the study of matter. Still, the line between organic and inorganic remained sharply drawn. Substances derived from living things, like oils, sugars, and proteins, were thought to be fundamentally different from minerals or metals. The turning point arrived in the early 19th century, when a German chemist named Friedrich Wöhler performed a simple but revolutionary experiment. In 1828, while working with ammonium cyanate, an inorganic salt, he unexpectedly produced urea, a compound known only from biological sources. This was a shock to the scientific community. It challenged the doctrine of vitalism by showing that an organic compound could be created from non-living precursors. Wöhler himself wrote in surprise to his mentor, saying that he had created urea without the need for a life force. Although vitalism did not disappear overnight, this experiment marked the beginning of a profound shift. From that point forward, organic chemistry could be understood as the study of carbon-based compounds, not as the study of mysterious life forces. The walls separating living and non-living matter began to dissolve. From Wöhler's time onward, organic chemistry became a field defined by both practical discoveries and theoretical progress. Chemists began to recognize that carbon held unique abilities, unlike any other element. Its capacity to form four bonds, to connect with itself in chains and rings, and to build structures of extraordinary variety meant that carbon could serve as the backbone of life. This recognition gave birth to the systematic study of organic molecules, and slowly, functional groups, molecular formulas, and structural diagrams became the tools of explanation. By mid-19th century, figures such as Auguste Kekulet and Archibald Coupeau proposed the tetravalency of carbon, and the idea that carbon atoms could bond to one another in long chains. Kekulet's dreamlike vision of a snake biting its tail even inspired his representation of the benzene ring, a structure that became iconic in organic chemistry. The foundations of organic chemistry were not laid only in theory but also in industry and medicine. The extraction of dyes from coal tar in the 19th century created a boom in synthetic chemistry. William Perkins' accidental creation of Movane, the first synthetic dye, opened a world of possibilities for textiles, pharmaceuticals, and materials. As synthetic pathways expanded, chemists saw that organic chemistry was not merely about describing nature but also about reshaping it. From the laboratory came medicines, new materials, and industrial products that transformed society. The contrast between the natural and the artificial became blurred, and with each advance, the science of organic chemistry gained credibility, depth, and power. Another foundational aspect was the development of structural theory. Knowing that compounds existed was not enough, chemists sought to understand how atoms were arranged. Through patient experimentation, they began to deduce structural isomers, molecules with the same formula but different arrangements. This insight revealed that structure determined function, a theme that still runs through every corner of organic chemistry. Eventually, spectroscopy, crystallography, and other techniques confirmed these insights, but the earliest generations worked largely through deduction, logic, and careful observation. It is also important to see the foundation of organic chemistry not only as a historical timeline but as a philosophical shift. For centuries, humans believed that life stood apart from matter, that some divine spark separated the living from the non-living. The transition to modern organic chemistry was, in a sense, the triumph of continuity. Life was not separate from matter but an expression of it. Carbon, hydrogen, oxygen, and nitrogen, the building blocks of organic molecules, were elements found everywhere, arranged in countless variations. The same atoms that formed rocks and gases could also form cells, tissues, and even consciousness. This realization did not make life less wondrous, it made it more deeply connected to the fabric of the universe. As we reflect on these beginnings, the story of organic chemistry becomes less about cold facts and more about human curiosity. From vitalism to Wuhas-urea synthesis, from Kekule's ring structures to Perkin's dyes, the journey illustrates the power of persistence and imagination. The foundations remind us that science advances by questioning assumptions, by observing carefully, and by daring to experiment. What once seemed impossible, to create organic compounds without life, became not only possible but routine. Today, entire industries rely on this ability, from pharmaceuticals to plastics, from agriculture to electronics. Yet beneath all these applications lies the same foundation, the recognition that organic chemistry is the study of carbon in its endless creativity. As you absorb this story, allow its calm rhythm to settle in your mind. You do not need to remember each name or date. Instead, hold on to the sense of transition, from mystery to clarity, from vitalism to material explanation, from separation to unity. These shifts form the ground upon which all further exploration of organic chemistry rests. As we move forward, the lecture will build upon this foundation, stepping into the details of atoms, bonds, and molecular shapes. For now, let this narrative rest within you, like the roots of a tree quietly nourishing what will grow above. To understand organic chemistry, we must begin with its smallest and most fundamental units, the atoms that make up every molecule. Atoms are often described as the building blocks of matter, but in the world of organic chemistry, they are much more than tiny spheres. They are dynamic, interactive, and governed by the rules of physics that shape how they bond together. The atom most central to this subject is carbon, but to appreciate its role, we must briefly look at the broader stage on which all atoms exist. Each atom is composed of a nucleus containing protons and neutrons, surrounded by electrons that occupy regions of space called orbitals. It is these electrons, especially those in the outermost shell, that determine how atoms connect with one another. In calm reflection, we can see the atom as both simple and profound, a small unit, yet capable of forming the complexity of life when arranged in vast combinations. Organic chemistry rests on the unique behavior of carbon, which has 4 electrons in its outer shell. This means carbon can form 4 bonds, a feature called tetravalency. Unlike many other elements, carbon does not simply form isolated units. It links to itself and to other atoms, creating chains, branches, and rings. This extraordinary flexibility allows it to serve as the backbone of molecules ranging from the simplest gases to the intricate architecture of proteins and DNA. Contrast this with oxygen, which has only 2 bonding sites, or hydrogen, which has 1. Carbon's ability to create stable yet versatile frameworks makes it the central character of organic chemistry. When you imagine molecules, you can picture carbon atoms as the scaffolding, holding everything together while allowing endless variations in form. At the heart of atomic interactions lie bonds. A bond is not a physical object but rather a stable arrangement of electrons that holds atoms together. The most important type for organic chemistry is the covalent bond, in which atoms share electrons. Sharing creates balance, allowing atoms to reach a stable configuration. For example, a hydrogen atom, with 1 electron, pairs with another hydrogen atom to share 2 electrons, forming the stable molecule H. In organic molecules, covalent bonds are everywhere, between carbon and hydrogen, between carbon and carbon, and between carbon and heteroatoms like oxygen, nitrogen, or sulfur. To contrast, ionic bonds, common in salts like sodium chloride, involve the complete transfer of electrons, creating oppositely charged ions that attract one another. While ionic bonds are strong in crystals, they are less central to organic structures. It is the sharing, the cooperation of covalent bonds, that gives organic molecules their character. The nature of covalent bonds depends not only on the number of shared electrons but also on their distribution. A single bond involves 2 electrons, a double bond 4, and a triple bond 6. As bonds multiply, they become shorter and stronger, but also less flexible. A single bond allows free rotation, like a hinge between 2 atoms, while a double bond locks atoms in place, creating rigidity. This difference plays a crucial role in how molecules behave. Consider ethane, with a carbon-U-carbon single bond, where the molecule can rotate freely, versus ethene, with a carbon-U-carbon double bond, which remains planar and rigid. Such contrasts in structure affect reactivity, stability, and biological function. In this way, even small differences at the atomic level ripple outward to shape the entire world of chemistry. To truly grasp the shapes of molecules, we turn to the concept of hybridization. Atoms do not simply hold electrons in neat, static boxes. Instead, their orbitals mix to form hybrid orbitals that allow for specific bonding geometries. For carbon, 3 major types of hybridization exist: sp³, sp², and sp. In sp³ hybridization, carbon forms 4 single bonds, arranged in a tetrahedral geometry with bond angles of about 109.5 degrees. This is the shape of methane, CH, the simplest hydrocarbon. In sp² hybridization, carbon forms 1 double bond and 2 single bonds, creating a trigonal planar shape with 120-degree bond angles, as seen in ethene. In sp hybridization, carbon forms 2 double bonds or 1 triple bond, leading to a linear structure with 180-degree bond angles, as in ethine. These shapes are not arbitrary, they minimize electron repulsion, following the principle that electrons arrange themselves as far apart as possible. By visualizing these geometries, we see not just atoms connected, but 3-dimensional frameworks that dictate molecular identity. Polarity further deepens our understanding of bonds. Not all covalent bonds share electrons equally. When atoms with different electronegativities bond, the more electronegative atom pulls electrons closer, creating a dipole. This partial separation of charge gives molecules unique properties. For example, in water, oxygen is more electronegative than hydrogen, so the bond is polar, leading to the remarkable ability of water to dissolve many substances. In organic chemistry, polar bonds between carbon and oxygen or carbon and nitrogen often dictate reactivity. Molecules with polar bonds interact with solvents differently than non-polar molecules, influencing solubility, melting points, and chemical behavior. Contrast polar ethanol, which mixes easily with water, with non-polar hexane, which separates into its own layer. These differences are subtle at the atomic level but dramatic in everyday experience. When we step back and consider molecular shapes, we notice that geometry is more than just an arrangement of atoms, it is a key to function. The 3-dimensional structure of molecules determines how they interact, how they fit together, and how they respond in reactions. A tetrahedral carbon in a drug molecule may align perfectly with a biological receptor, while a flat, planar structure may not. This lock-and-key principle underlies the activity of countless molecules in biology and medicine. Even molecules with the same atoms, if arranged differently, may behave in entirely different ways, an idea that leads us toward the topic of isomerism in later sections. For now, it is enough to see that the shape of a molecule is as crucial as the atoms within it. Understanding atoms, bonds, and molecular shapes lays the foundation for everything else in organic chemistry. These concepts, though abstract at first, reveal a world of balance and contrast. Sharing versus transferring electrons, flexible single bonds versus rigid double bonds, polar versus non-polar interactions, each of these contrasts becomes a recurring theme. Together, they form a calm, logical framework that supports the vast forest of organic chemistry. As you let these ideas sink in, remember that you do not need to memorize them all at once. Instead, allow the rhythm of the words to form gentle associations. The atom is the seed, the bond is the stem, and the geometry is the branching pattern that grows into the molecule. From these quiet beginnings, the complexity of life emerges. As the lecture moves forward, we will expand into functional groups, the vocabulary of organic chemistry, where these atomic patterns come alive in recognizable families. For now, let your mind rest in the simplicity of atoms and their elegant bonds, the shapes they create, and the harmony they reveal. In organic chemistry, once we have understood atoms, bonds, and shapes, the next step is to recognize recurring patterns. These patterns are called functional groups, and they serve as the basic vocabulary of the subject. Functional groups are specific arrangements of atoms within molecules that give those molecules their characteristic properties. By learning them, we create a mental dictionary, a way to quickly recognize what a molecule can do, how it might behave, and how it might interact with others. This is why functional groups are sometimes called the alphabet of organic chemistry. Each one is like a letter or a syllable, and by combining them, we create the countless words of molecular structures. Knowing functional groups allows us to look at a complex molecule and immediately see meaning rather than confusion. The simplest category begins with hydrocarbons, molecules made only of carbon and hydrogen. Within this group, we find alkanes, alkenes, alkynes, and aromatic compounds. Alkanes contain only single bonds, and they are saturated, meaning no additional hydrogens can be added without breaking bonds. They are generally unreactive, serving as a stable background in many molecules. Alkenes, by contrast, contain double bonds. That extra bond gives them reactivity, making them important in polymer formation and many natural processes. Alkynes go further with triple bonds, linear in shape and often even more reactive. Aromatic compounds, such as benzene, are unique. Despite having alternating double bonds, they achieve remarkable stability through resonance, spreading electron density evenly across the ring. These hydrocarbon functional groups form the skeleton of organic chemistry, the basic framework upon which other functional groups are attached. Moving beyond hydrocarbons, we find groups containing oxygen. Alcohols are among the most familiar, characterized by an hydroxy group attached to a carbon. They range from simple methanol and ethanol to complex biomolecules. Alcohols often form hydrogen bonds, making them soluble in water and giving them distinctive boiling points. Closely related are ethers, where an oxygen atom links two carbons. Ethers are less reactive, often serving as solvents in laboratories. Carbonyl groups are another vital class, where a carbon atom is double bonded to an oxygen. Depending on what else is attached, the carbonyl appears in aldehydes, ketones, carboxylic acids, esters, or amides. Each of these subgroups behaves differently, yet they all share the polar nature of the carbon-oxygen double bond. Aldehydes and ketones are common in flavors and fragrances, while carboxylic acids give sourness to foods like vinegar and are essential building blocks in metabolism. Esters, formed from acids and alcohols, are known for their pleasant fruity scents. Amides, linking acids, and amines form the backbone of proteins, giving structure to life itself. Nitrogen also plays an important role in functional groups. Amines are compounds in which nitrogen bonds to carbon and hydrogen, resembling ammonia but modified with organic groups. They are basic, capable of accepting protons, and they occur widely in biological molecules, including neurotransmitters like serotonin and dopamine. Amides, as mentioned before, connect nitrogen with a carbonyl group, creating bonds that are strong and stable, essential for proteins. Nitriles, containing a carbon-nitrogen triple bond, add another layer of diversity, often appearing in synthetic materials and pharmaceuticals. The presence of nitrogen frequently changes the behavior of molecules dramatically, making them biologically active and chemically versatile. Halogens, fluorine, chlorine, bromine, and iodine also create distinct functional groups when bonded to carbon. These halogenated compounds vary in reactivity and are used in solvents, refrigerants, and pharmaceuticals. A carbon-halogen bond is polarized, with the halogen pulling electrons toward itself, and this polarity often makes these molecules reactive in substitution or elimination reactions. Though some halogenated compounds are useful, others pose environmental concerns, reminding us of the responsibility that comes with chemical knowledge. Another key set of functional groups includes those with sulfur and phosphorus. Phenols, similar to alcohols but with sulfur in place of oxygen, have strong odors, often associated with garlic or skunk spray. Sulfides parallel ethers, while disulfides play a crucial role in stabilizing protein structures. Phosphates are central to energy transfer in biology, most famously in adenosine triphosphate, or ATP. These groups remind us that while carbon is the backbone, other elements shape the diversity of organic chemistry in profound ways. Functional groups do more than just define classes of molecules, they determine reactivity. A molecule's chemical behavior is dictated largely by the functional groups it contains. An alcohol tends to undergo oxidation, turning into an aldehyde or ketone, while an alkene tends to undergo addition reactions, breaking the double bond to form new products. Carboxylic acids behave as acids, donating protons, while amines behave as bases, accepting them. By identifying functional groups, chemists can predict reactions without needing to memorize every single compound. This predictive power is why functional groups are emphasized so strongly in the study of organic chemistry. They provide order to what might otherwise appear chaotic. Functional groups also reveal the deep connection between organic chemistry and everyday life. Consider ethanol, the alcohol in beverages, and acetic acid, the main component of vinegar. One contains an hydroxy group, the other a ECOH group, and from these small differences arise entirely different properties and uses. The fragrance of fruits often comes from esters, while the sharp smell of nail polish remover comes from acetone, a ketone. Proteins, carrying out nearly every function in living organisms, are built from amides. Even DNA, the molecule of heredity, is full of functional groups, phosphates in the backbone, carbonyls and amines in the bases, that determine its ability to store and transmit information. By learning these patterns, we see how the abstract world of chemistry connects intimately with the sensory world we experience. It is also useful to appreciate functional groups through contrasts. Hydrocarbons versus oxygenated groups, polar versus nonpolar, acidic versus basic, stable versus reactive, these pairings help the mind anchor knowledge. Just as a calm night is best understood when compared with a bright day, so too does the acidic bite of a carboxyl group become clearer when contrasted with the inert nature of an alkane. These contrasts do not complicate learning. Instead, they simplify it by offering balance and perspective. As we conclude this section, let the idea settle that functional groups are not random details but recurring motifs. They are the recurring musical notes in the symphony of organic chemistry. By recognizing them, you begin to hear the melody rather than noise. Every molecule, no matter how large or complex, can be broken down into these familiar parts. With time, they become second nature, like letters forming words, words forming sentences, and sentences forming meaning. Allow these ideas to rest in your mind like gentle patterns. In the next stage of this lecture, we will turn to hydrocarbons themselves, the skeletons of organic molecules, and see how these frameworks expand into the diversity of life and materials. For now, you can simply relax with the knowledge that you have started to build a vocabulary, a language that will guide you deeper into the subject. Hydrocarbons form the most fundamental skeletons of organic chemistry. They are composed of only two elements, carbon and hydrogen, yet from this apparent simplicity arises immense diversity. By arranging carbons in chains, branches, rings, and networks, and by varying the types of bonds between them, nature and human creativity have produced countless molecules. Hydrocarbons serve as the core structures upon which other functional groups attach, and they are also important on their own, giving rise to fuels, solvents, and materials that define daily life. To approach hydrocarbons calmly is to begin with their most basic forms and gradually build toward complexity, seeing how each variation changes the behavior of molecules while still remaining rooted in the same essential framework. The simplest hydrocarbons are alkanes, sometimes called saturated hydrocarbons. They contain only single bonds between carbon atoms, and each carbon is bonded to as many hydrogens as it can accommodate. Methane, CH, is the smallest and simplest member, a single carbon surrounded by 4 hydrogens. Ethane, propane, and butane extend the chain 1 carbon at a time. With each step, new possibilities emerge: longer chains, branching points, and even rings. The general formula for alkanes is CnH2n+2, and this formula reflects their fully saturated nature. Alkanes are relatively unreactive because their carbon-U-carbon and carbon-E hydrogen single bonds are stable. They burn readily, releasing energy, which is why they are used as fuels. The gas in stoves, the fuel in lighters, and the propane in camping tanks are all examples. In this way, the calm stability of alkanes becomes energy when released through combustion. As chains lengthen, alkanes demonstrate the principle of isomerism. Butane, for example, can exist as a straight chain or as a branched form called isobutane. Both have the same formula, CH, but their structures differ, and so do their properties. Branching lowers boiling points, changes density, and alters how molecules pack together. These differences highlight how hydrocarbons are not merely collections of atoms but three-dimensional structures whose shapes influence their behavior. When chains form rings, we encounter cycloalkanes, such as cyclopentane or cyclohexane. These ring structures are important in biology and industry, offering rigidity compared to flexible chains. In this way, even the simple alkane family illustrates the richness that arises from carbon's bonding versatility. When one of the carbon-E-carbon single bonds becomes a double bond, we enter the family of alkenes. The general formula shifts to CnH2n, reflecting the reduction in hydrogens due to the double bond. This double bond changes the behavior of the molecule dramatically. Unlike single bonds, double bonds are rigid, preventing rotation and locking atoms in place. This rigidity introduces geometric isomerism, where molecules differ in the arrangement of groups around the double bond. For example, in 2-butene, substituents can be on the same side, called cis, or on opposite sides, called trans. These geometric isomers have different properties, and the cis-trans distinction is critical in biological molecules, influencing shapes of fats and behaviors of membranes. Alkenes are also more reactive than alkanes, participating in addition reactions where new atoms attach to the carbons of the double bond. This reactivity makes alkenes important intermediates in polymer production, such as polyethylene, which is made from ethene units joined together. Thus, alkenes show us how a simple change in bonding leads to new properties, reactivity, and uses. Further along the spectrum are alkynes, which contain triple bonds. Their formula is CnH2n2, reflecting the presence of even fewer hydrogens. Triple bonds are linear, creating straight geometries, and they hold carbons tightly together with great bond strength. This strong bonding makes alkynes highly reactive in specific ways, often serving as starting points for chemical synthesis. Acetylene, the simplest alkyne, has long been used as a fuel for welding because of its intense flame when burned with oxygen. The linearity of alkynes contrasts with the tetrahedral shapes of alkanes and the planar nature of alkenes, reminding us again that carbon's bonding versatility creates a spectrum of geometries. Each geometry has its own consequences for reactivity and function. One of the most fascinating categories of hydrocarbons is the aromatic family, exemplified by benzene. At first glance, benzene appears to be a 6-carbon ring with alternating single and double bonds. However, its true nature is more subtle. The electrons in those bonds are delocalized, spread evenly around the ring, creating a stable system of resonance. This delocalization gives benzene unusual stability, far greater than a simple combination of alternating bonds would predict. Aromatic compounds play central roles in biology and industry. They form the basis of many natural products, pharmaceuticals, and materials. The fragrant molecules that give flowers and spices their scents, the pigments that provide color, and the structures of DNA bases all rely on aromatic chemistry. The term aromatic originally referred to their smell, but today it refers to this special electron delocalization that creates a stable and unique type of hydrocarbon. By looking at alkanes, alkenes, alkynes, and aromatics together, we see a progression from stability to reactivity, from flexibility to rigidity, from saturation to delocalization. Alkanes are stable and saturated, resistant to reaction but full of stored energy. Alkenes add reactivity, offering double bonds that can be attacked and transformed. Alkynes intensify this with triple bonds, linear and energetic. Aromatics then circle back to stability, but in a new form, stability not from saturation, but from resonance. These contrasts give us a map of hydrocarbon chemistry, a way to navigate their variety without feeling lost. Hydrocarbons also illustrate the interplay between natural occurrence and human use. Natural gas is composed largely of methane, ethane, propane, and butane. Crude oil contains a vast mixture of hydrocarbons that can be distilled into fuels like gasoline, kerosene, and diesel. Alkenes serve as raw materials for plastics, while aromatics provide the foundation for dyes and pharmaceuticals. In biology, hydrocarbons appear in lipids, the molecules that store energy and form cell membranes. Fatty acids contain long hydrocarbon chains, sometimes with double bonds that determine whether they are saturated or unsaturated fats. These variations influence the fluidity of membranes and the health impacts of dietary fats. Thus, hydrocarbons are not abstract categories but central components of energy, materials, and life itself. The study of hydrocarbons also introduces the principle of substitution, where hydrogen atoms can be replaced by other functional groups. This is how the skeleton of hydrocarbons expands into the broader world of organic molecules. An alkane may become an alcohol by replacing a hydrogen with a hydroxyl group, or it may become a halogenated compound by substituting chlorine. The hydrocarbon framework provides the backbone, and functional groups provide the decorations. By first appreciating the skeleton itself, we can later understand how it combines with other features to create the full diversity of organic chemistry. The skeleton is simple, yet it carries endless potential for elaboration. As this section concludes, allow the ideas of hydrocarbons to rest gently in your mind. From the simple calmness of methane to the resonance of benzene, from flexible chains to rigid rings, the story of hydrocarbons reveals the creative possibilities of carbon. They form the skeleton upon which all else is built, a framework both stable and adaptable. By seeing their categories clearly, alkanes, alkenes, alkynes, and aromatics, you hold a map that will guide you deeper into the subject. The next step in our journey will be to explore stereochemistry and isomerism, the subtle art of how the same atoms can arrange themselves differently, leading to profound differences in behavior. For now, let the calm symmetry of hydrocarbons settle into your memory, a reminder that even the simplest frameworks can give rise to infinite variety. As we move deeper into the world of organic chemistry, we encounter one of its most fascinating dimensions: the idea that molecules with the same atoms and the same overall formula can exist in different forms. This phenomenon is called isomerism, and it reminds us that chemistry is not only about what atoms are present but also about how they are arranged in space. Just as two houses built with the same bricks can look entirely different depending on their design, molecules built from the same atoms can display completely different properties depending on their arrangement. This concept of isomerism is central to understanding the diversity of organic chemistry, and it becomes even more striking when we explore stereochemistry, the study of how molecules exist and interact in three-dimensional space. The most basic kind of isomerism is structural isomerism. In this case, the atoms are connected in different orders, creating different skeletons even though the formulas are identical. Consider butane, with the formula CH. It can exist as a straight chain, where all four carbons are in a row, or as isobutane, where three carbons form a chain and the fourth branches off from the middle carbon. These two molecules share the same number of carbons and hydrogens, yet their boiling points, densities, and chemical behaviors are not the same. This simple example shows how arrangement matters, even when the ingredients are unchanged. The principle of structural isomerism extends to larger molecules, where the number of possible arrangements grows rapidly, adding complexity and diversity to the organic world. Beyond structural differences, molecules can also differ in their three-dimensional orientation, giving rise to stereoisomers. Unlike structural isomers, stereoisomers have the same connectivity of atoms but differ in the way those atoms are positioned in space. One important type of stereoisomerism is geometric isomerism, often seen in alkenes. Because a carbon-to-carbon double bond does not allow free rotation, groups attached to the carbons may either lie on the same side or on opposite sides. When they are on the same side, the molecule is called a cis isomer. When they are opposite, it is called a trans isomer. Although the difference may appear subtle, it can have significant effects. For example, cis-2-butene and trans-2-butene have slightly different boiling points and different stabilities. In biological systems, the cis or trans arrangement of double bonds in fatty acids influences the fluidity of cell membranes and even the health effects of dietary fats. This is a reminder that small geometric shifts can carry large consequences. The most intriguing type of stereoisomerism, however, arises from chirality. A molecule is chiral if it cannot be superimposed on its mirror image, much like how your left hand and right hand are mirror images but not identical. Chiral molecules contain a carbon atom bonded to 4 different substituents, creating what is called a chiral center or stereocenter. The 2 mirror image forms are called enantiomers. Though enantiomers share the same connectivity and often identical physical properties like boiling points or solubility, they differ profoundly in the way they interact with other chiral systems, especially biological ones. For example, one enantiomer of the molecule carvone smells like spearmint, while its mirror image smells like caraway. The difference arises because our noses, like much of biology, are chiral systems that distinguish between left and right-hand molecules. In medicine, the importance of chirality is even more dramatic. The drug thalidomide, prescribed in the 1950s as a sedative, existed in 2 enantiomeric forms. One form was therapeutic, while the other caused severe birth defects. This tragedy highlighted the need for chemists to carefully consider chirality in drug design and synthesis. Many modern drugs are produced as single enantiomers to ensure safety and effectiveness. The story of chirality shows us how subtle differences in molecular arrangement can mean the difference between healing and harm, fragrance and foulness, safety and danger. It is a vivid reminder of why stereochemistry is not just abstract theory but a matter of profound real-world importance. Another category of stereoisomers includes diastereomers, which are stereoisomers that are not mirror images. Unlike enantiomers, diastereomers have different physical properties, such as melting points and solubilities, and they can often be separated by conventional means. Diastereomers arise in molecules with multiple chiral centers, where flipping one center but not another creates new variations. For example, sugars like glucose and galactose share the same formula but differ in the arrangement around a single stereocenter. These differences are small in one sense, yet they change how the body metabolizes them, how they taste, and how they participate in biological pathways. Diastereomers, therefore, add another layer of richness to the stereochemical landscape. Stereochemistry extends further into the way molecules interact with light. Chiral molecules rotate plane polarized light, a property known as optical activity. One enantiomer rotates light to the right, called dextrorotatory, while the other rotates it to the left, called levorotatory. Measuring this rotation allows chemists to distinguish between enantiomers, even when other properties are identical. In a calm way, we can imagine these molecules as dancers moving in opposite directions, each responding to light differently, each leaving its own subtle imprint on the world. The importance of stereochemistry is deeply tied to biology, because life itself is stereospecific. Proteins are made from amino acids that are all left-handed, while sugars in DNA and RNA are all right-hand. This uniformity, called homochirality, is one of the great mysteries of the origin of life. Why did life choose one-handedness over the other? The answer is not fully known, but the fact that it did shows how stereochemistry permeates every level of living systems. From the twisting double helix of DNA to the folded structures of proteins, stereochemistry gives form, direction, and specificity. When we reflect on isomerism and stereochemistry, we see once again the power of contrast. Structural isomers versus stereoisomers, cis versus trans, left-handed versus right-hand, enantiomers versus diastereomers. These contrasts may seem subtle, yet they make the difference between molecules that are inert and those that are active, between those that nourish life and those that harm it. This duality, this play of mirrored forms and rigid geometries, gives organic chemistry its depth and beauty. As you let these ideas settle, imagine molecules not as flat drawings on paper but as living forms in 3 dimensions, turning, twisting, mirroring, and interacting. Stereochemistry is the art of space within chemistry, the recognition that position and orientation matter just as much as composition. This awareness prepares us for the next stage of the journey, where we will examine reactions themselves, the ways in which molecules transform, rearrange, and evolve. For now, let the calm symmetry and subtle differences of isomerism rest in your thoughts, like mirrored reflections on a still pond, similar yet never identical. Organic chemistry is not only about recognizing molecules and their structures but also about understanding how those molecules change. Reactions are the heart of the subject, the movements through which molecules transform into new forms. When we study organic reactions, we are not simply memorizing lists but learning patterns that repeat across countless situations. These patterns reveal the logic of molecular change, and once we recognize them, the subject becomes less overwhelming and more like learning a language. Just as sentences are built from verbs that show action, reactions are the verbs of chemistry, showing what molecules can do. By seeing the big picture of organic reactions, we learn how molecules rearrange, how bonds break and form, and how energy flows through matter. One of the most common categories of organic reactions is substitution. In a substitution, one group in a molecule is replaced by another. Imagine a dance where one partner steps aside and another takes their place. In molecules, a leaving group departs, and a new group attaches to the same carbon. There are different mechanisms for substitution, often labeled as SN1 and SN2. In SN1, the process occurs in 2 steps. First, the leaving group detaches, creating a temporary carbocation, and then the new group attaches. This mechanism depends on the stability of the carbocation, so tertiary carbons, which stabilize positive charge, favor SN1. In SN2, by contrast, the substitution happens in a single step, with the new group pushing the old one out at the same time. This mechanism requires an unhindered carbon, so primary carbons favor SN2. The distinction between SN1 and SN2 highlights the balance between stability and accessibility, 2 themes that reappear throughout organic chemistry. Another central category is elimination. In elimination reactions, instead of replacing a group, a molecule loses atoms, often forming a double bond. It is as though the molecule simplifies itself, shedding weight to create a leaner, more reactive form. Elimination often competes with substitution, since both involve leaving groups. In E1 eliminations, the process occurs in 2 steps, beginning with the formation of a carbocation, much like SN1. In E2 eliminations, the process occurs in a single step, with a base removing a proton as the leaving group departs, forming a double bond instantly. The outcome, whether substitution or elimination occurs, depends on conditions such as the strength of the base, the structure of the carbon, and the temperature. This competition between pathways reflects the dynamic nature of chemistry, where multiple possibilities coexist and conditions tilt the balance. Addition reactions provide another fundamental pattern, especially for molecules with double or triple bonds. In addition, new atoms or groups are added across the multiple bond, converting it into single bonds. For example, in the hydrogenation of an alkene, hydrogen atoms add across the double bond, turning it into an alkane. In halogenation, chlorine or bromine adds across the bond, creating dihalides. Addition reactions are essential for polymerization, where small units link together to form massive chains. The softness of polyethylene bags or the strength of synthetic rubbers begins with simple addition reactions repeated countless times. Additions highlight the reactivity of unsaturated hydrocarbons, showing how molecules that contain double or triple bonds are gateways to transformation. Oxidation and reduction reactions introduce another layer of change. In organic chemistry, oxidation generally means increasing the number of bonds to oxygen or other electronegative elements, while reduction means increasing bonds to hydrogen. For instance, alcohols can be oxidized to aldehydes or ketones, and further to carboxylic acids. Conversely, carbonyl compounds can be reduced back to alcohols. These changes are not only central to laboratory chemistry but also to metabolism in living organisms. The burning of glucose for energy is essentially a series of controlled oxidation reactions, while photosynthesis reverses this by reducing carbon dioxide to glucose. The balance between oxidation and reduction is one of nature's great cycles, keeping life in motion. Another important class of reactions is rearrangements. In these, atoms within a molecule shift positions, creating a new structure without changing the overall formula. Rearrangements may occur during other reactions, as intermediates reorganize themselves to achieve greater stability. A carbocation may move from one carbon to another if it creates a more stable arrangement, and groups may migrate within a molecule, leading to surprising products. These internal shifts remind us that molecules are not fixed but dynamic, always seeking the lowest energy state. Rearrangements illustrate how even within the same set of atoms, new forms can emerge simply by changing connections. When we step back, we can see that these categories, substitution, elimination, addition, oxidation reduction, and rearrangement, form the core grammar of organic chemistry. Rather than treating each reaction as unique, we can understand them as variations on themes. Substitution exchanges partners, elimination creates double bonds, addition breaks them, oxidation and reduction shift balance between oxygen and hydrogen, and rearrangements reorganize structure. These patterns repeat across molecules, providing a sense of order. By learning the big picture, we reduce the chaos of thousands of named reactions to a few broad families. The importance of these reaction types becomes clear when we connect them to real life. Substitution reactions lie at the heart of pharmaceuticals, where functional groups are swapped to modify activity. Elimination reactions produce alkenes, which serve as starting materials for plastics. Addition reactions create polymers, the basis of countless synthetic materials. Oxidation and reduction govern energy flow in metabolism, from the breakdown of food to the generation of ATP. Rearrangements underlie many biosynthetic pathways, where molecules shift and fold to create the complexity of natural products. These everyday connections anchor abstract reactions in tangible reality. It is helpful to notice the contrasts between these reaction families. Substitution versus elimination, addition versus elimination, oxidation versus reduction. These pairings are opposites, each balanced against its counterpart. Substitution brings something in, elimination takes something away. Addition increases saturation, elimination creates unsaturation. Oxidation strips electrons, reduction restores them. These contrasts form a rhythm, a balance that echoes through organic chemistry. By thinking in pairs, we create mental anchors that guide our understanding. As you let these patterns settle, remember that the goal is not to memorize every detail but to recognize the logic of change. Molecules behave in ways that are consistent and predictable once you see the themes. Organic reactions are not chaotic storms but graceful dances, each move governed by rules of stability, energy, and geometry. By appreciating the big picture, you prepare yourself for the next step, which is to look closely at the mechanisms, the step-by-step pathways by which these transformations occur. For now, let the calm rhythm of reactions rest in your thoughts, a reminder that change is not random but structured, a language waiting to be learned slowly and patiently. When we study reactions in organic chemistry, it is not enough to know only the starting materials and the final products. To truly understand, we must look at the journey between those 2 points, the step-by-step path that molecules take as bonds break, new bonds form, and electrons move. This detailed story of change is what chemists call a reaction mechanism. Mechanisms reveal the hidden choreography of atoms and electrons, and by following them we learn not just what happens, but how and why it happens. Understanding mechanisms allows us to predict outcomes, design new reactions, and connect the language of organic chemistry to the processes of life and industry. At the heart of every mechanism is the movement of electrons. Bonds form when electrons are shared, and bonds break when electrons shift. To visualize these changes, chemists often use curved arrows to show the flow of electron pairs. Though these arrows are drawn on paper, they represent real tendencies in the quantum world. Electrons seek regions of lower energy, moving from areas of high density to areas that can stabilize them. In this way, mechanisms are maps of electron behavior, showing us where the energy flows and how stability is achieved. Two recurring players in these mechanisms are nucleophiles and electrophiles. A nucleophile is an electron-rich species, often carrying a negative charge or a lone pair of electrons. It seeks out positive or electron-poor regions, acting like a donor. An electrophile, by contrast, is electron-poor, attracted to areas rich in electrons. It acts like an acceptor. When nucleophiles and electrophiles meet, bonds form. This simple dynamic explains a vast number of organic reactions. For example, a hydroxide ion, with its electron-rich oxygen, is a strong nucleophile. A carbocation, with its electron-deficient carbon, is a strong electrophile. Their interaction, though simple, illustrates the push and pull of electrons that drives much of organic chemistry. As molecules react, they often pass through intermediate stages, temporary structures that exist only along the way from reactant to product. One common type of intermediate is the carbocation, a positively charged carbon with only 6 electrons instead of the usual 8. Carbocations are unstable and reactive, but their stability varies depending on their environment. Tertiary carbocations, surrounded by 3 other carbons, are more stable than secondary or primary ones, because neighboring carbons help disperse the positive charge. Radicals, species with unpaired electrons, are another type of intermediate, playing key roles in certain reactions such as halogenation. Carbanions, with negatively charged carbons, also arise under specific conditions. Though fleeting, these intermediates guide the course of reactions, and their stability often determines which pathway a mechanism follows. Another key concept is the transition state. Unlike intermediates, which can sometimes be isolated or observed, a transition state is purely theoretical. It represents the highest energy arrangement of atoms along the path of a reaction, the point of maximum strain before the system relaxes into a more stable form. Transition states are like the peak of a hill between 2 valleys. The molecule must climb up to this point before rolling down into the product state. The height of this hill determines the rate of the reaction. A lower energy transition state means the reaction proceeds quickly, while a higher one slows it down. By understanding transition states, chemists can explain why some reactions are fast and others sluggish, and how catalysts lower energy barriers to speed up transformations. Mechanisms also help us understand the competition between different pathways. In many cases, the same starting material can undergo more than one reaction, depending on conditions. For example, an alkyl halide exposed to a strong nucleophile may undergo substitution, while in the presence of a strong base at higher temperature it may undergo elimination instead. The mechanism shows why. In one pathway, the nucleophile attacks the carbon directly. In the other, the base abstracts a proton, leading to a double bond. Both possibilities are encoded in the electron arrangements, and the mechanism allows us to see the branching points clearly. This predictive power is one of the greatest strengths of mechanistic thinking. Energy diagrams are often used to visualize these steps. The vertical axis represents energy, while the horizontal axis represents the progress of the reaction. Reactants begin at one level, climb up to the transition state, and descend to the products. If intermediates exist, the diagram shows multiple hills and valleys, each corresponding to a stage in the mechanism. These diagrams provide a calm way to see the entire journey at once, showing how energy shapes the path. Exothermic reactions, which release energy, end at a lower energy level than they began, while endothermic reactions, which absorb energy, end higher. By combining these diagrams with arrow pushing, chemists create a clear and detailed picture of how reactions unfold. Mechanisms are not abstract inventions, they explain real processes all around us. In biology, enzyme-catalyzed reactions follow precise mechanisms, where active sites stabilize transition states and guide intermediates. In industry, mechanisms reveal how catalysts transform raw materials into fuels, plastics, and medicines. Even the simple act of burning a candle involves radical mechanisms as hydrocarbons react with oxygen. By studying mechanisms, we connect the microscopic world of electrons to the macroscopic world of life and technology. It is also helpful to view mechanisms through contrasts. Stepwise versus concerted, substitution versus elimination, radical versus polar, stable intermediates versus fleeting transition states. Each contrast frames the patterns more clearly, helping us see how pathways diverge and converge. These contrasts provide balance, turning what might seem like endless details into a series of themes. As you let these ideas rest, think of mechanisms not as burdensome details but as stories of transformation. Each step is a scene, each arrow a movement, each intermediate a character on the stage. Together they form a narrative of change, unfolding slowly but with purpose. By learning mechanisms, we learn to read the stories molecules tell, to see not only where they begin and end but how they move through the world. As we move forward, we will connect these mechanistic insights to the role of organic molecules in life itself, where reactions give rise to energy, structure, and meaning. For now, let the calm flow of electrons and the gentle rhythm of molecular change settle into your thoughts, preparing you for the next chapter of this journey. Organic chemistry is not just a subject confined to laboratories, textbooks, or abstract reactions. It is the living fabric of biology, the chemistry of life itself. Every process that sustains us, from the breath we take to the energy we use to move, rests on organic molecules and their interactions. By looking at the role of organic chemistry in life processes, we see that it is not distant or separate from us but intimately connected to our daily existence. To approach this subject calmly, we begin with the essential biomolecules, carbohydrates, lipids, proteins, and nucleic acids, and then explore how they interact to create the miracle of life. Carbohydrates are among the simplest and most immediate sources of energy for living systems. They are composed of carbon, hydrogen, and oxygen, usually in the ratio that resembles water, with general formulas close to CnH2 non. Glucose, the most familiar carbohydrate, serves as the fuel that cells rely on to produce energy. When glucose is broken down through cellular respiration, energy is released in controlled steps and captured in the form of adenosine triphosphate, or ATP. This energy currency powers countless processes, from muscle contraction to nerve transmission. Carbohydrates also provide structural roles. In plants, cellulose forms the rigid framework of cell walls, while in animals, complex carbohydrates contribute to connective tissues. The dual nature of carbohydrates, fuel for energy and material for structure, shows their central role in both stability and dynamism. Lipids, another class of organic molecules, are built primarily from long hydrocarbon chains. These chains make them hydrophobic, meaning they do not mix well with water, and this property gives them unique biological roles. Fats and oils serve as concentrated energy stores, packing more calories per gram than carbohydrates. Phospholipids, with hydrophobic tails and hydrophilic heads, form the bilayers that make up cell membranes. This self-assembly into membranes creates the boundary between life and the outside world, defining the space in which cells can exist. Cholesterol, another lipid, is often misunderstood, yet it is essential for maintaining membrane fluidity and serving as a precursor to hormones such as estrogen and testosterone. In these ways, lipids are not just passive stores of energy but active architects of life's boundaries and signals. Proteins take us further into the complexity of organic chemistry in biology. Composed of chains of amino acids linked by amide bonds, proteins fold into precise three-dimensional structures. The sequence of amino acids determines the folding, and the folding determines the function. Enzymes, a class of proteins, act as catalysts, lowering the energy barriers for reactions and guiding molecules along specific pathways. Without enzymes, the chemistry of life would proceed too slowly to sustain existence. Proteins also provide structural support, as in collagen, and allow for movement, as in actin and myosin in muscles. Hemoglobin, a protein in red blood cells, carries oxygen throughout the body. Antibodies defend us against infections. The diversity of proteins illustrates the power of organic chemistry to generate complexity from simple building blocks. By varying the sequence of just 20 amino acids, living systems create an almost infinite variety of forms and functions. Nucleic acids complete the set of fundamental biomolecules. DNA and RNA are polymers of nucleotides, each composed of a sugar, a phosphate group, and a nitrogenous base. The sequence of bases encodes information, the blueprint of life. DNA stores the instructions for building proteins, while RNA plays multiple roles, from carrying messages to catalyzing reactions. The double helix of DNA, with its complementary base pairing, ensures faithful replication and inheritance. This elegant structure, built on hydrogen bonds and stacking interactions, shows the delicate balance of forces at work in organic chemistry. Life's continuity rests on the ability of nucleic acids to store, copy, and transmit information across generations. When we look at metabolism, we see organic chemistry in constant motion. Glucose enters the glycolytic pathway, breaking down into pyruvate and releasing energy. Pyruvate enters the citric acid cycle, producing carbon dioxide and capturing more energy. Electrons are transferred along the electron transport chain, driving the production of ATP. These cycles are chains of organic reactions, carefully regulated by enzymes, balancing oxidation and reduction. The flow of energy through metabolism mirrors the flow of electrons in organic reactions, showing the deep connection between fundamental chemical principles and the processes of life. Organic chemistry also underlies communication within and between cells. Hormones, many of them small organic molecules, act as messengers, traveling through the bloodstream to regulate growth, metabolism, and mood. Neurotransmitters, such as serotonin, dopamine, and acetylcholine, are organic compounds that carry signals across synapses in the brain. Even the senses we use to experience the world, smell, taste, vision, depend on organic molecules interacting with receptors. The scent of a rose, the sweetness of sugar, the ability of retinal in the eye to change shape when struck by light, all of these are moments where organic chemistry becomes experience. Life processes also highlight the contrasts within organic chemistry. Carbohydrates provide quick energy, while lipids store it for the long term. Proteins act as catalysts and structures, while nucleic acids encode information. Hydrophilic molecules dissolve in water and move freely, while hydrophobic molecules cluster and form membranes. Oxidation breaks down molecules for energy, while reduction builds them back up in photosynthesis. These contrasts keep the balance of life, much like the balance of reactions in the laboratory. Recognizing them allows us to see not just the details but the harmony of the whole system. As we reflect on organic chemistry in life processes, we realize that every breath, every heartbeat, every thought is rooted in these molecules and their interactions. The glucose you eat becomes the energy to think and move. The lipids in your cells create the barriers that separate you from your environment. The proteins in your body carry out tasks with precision and speed, while your DNA quietly stores the instructions for it all. These molecules do not exist in isolation, they form a network, a web of interactions that together create the phenomenon we call life. Let these ideas settle gently, as if seeing the invisible threads that weave through living systems. You do not need to recall every pathway or every molecule in detail. Instead, hold the calm awareness that life itself is a manifestation of organic chemistry, that the same principles of bonds, structures, and reactions we have studied flow through you at every moment. With this perspective, we are ready to move forward to the role of organic molecules in the wider world of materials, polymers, and synthetic creations, where the same chemistry that builds life is used to build the modern world. Polymers are among the most remarkable achievements of organic chemistry, not because they are rare or complicated in principle, but because of how common and influential they are in both natural systems and human-made materials. A polymer is a large molecule made by linking many smaller repeating units, called monomers. This simple idea, that small molecules can join together to form long chains, has transformed the way life builds its own structures and the way humans design new materials. From the proteins in our bodies to the plastics in everyday life, polymers show how organic chemistry scales from the microscopic to the macroscopic, from the invisible world of atoms to the visible world of fibers, films, and solids. In nature, polymers form the backbone of biological structure and function. Proteins are polymers of amino acids, each linked by amide bonds in long chains that fold into precise three-dimensional shapes. These shapes give proteins their extraordinary variety of functions, from enzymes that speed up reactions to structural components that give strength to skin, hair, and connective tissue. Nucleic acids, DNA and RNA, are also polymers, built from repeating nucleotides. Their ability to store and transmit genetic information depends on the way these polymers arrange themselves in long sequences. Polysaccharides, such as starch, glycogen, and cellulose, are polymers of simple sugars. They store energy in plants and animals or provide strength and rigidity to plant cell walls. In every cell of every organism, polymers are at work, creating both stability and adaptability. Synthetic polymers, created by humans, reflect our attempt to imitate and extend nature's methods. In the 19th century, chemists began experimenting with polymerization, leading to the birth of the plastics industry. Polyethylene, one of the simplest synthetic polymers, is made by polymerizing ethene molecules. Depending on how it is processed, polyethylene can be soft and flexible, as in plastic bags, or strong and rigid, as in water pipes. Polystyrene, formed from styrene monomers, can be molded into solid materials or expanded into foams used in packaging. Nylon, one of the earliest synthetic fibers, was designed as an alternative to silk and remains essential in textiles today. These examples show how changing the monomer or the arrangement of chains leads to different properties, allowing polymers to be tailored for countless uses. The process of polymerization can proceed by different mechanisms. In addition, polymerization, unsaturated monomers, such as alkenes, join together by opening their double bonds and linking in chains. This is how polyethylene and polypropylene are formed. In condensation polymerization, monomers join by eliminating small molecules, such as water or methanol, as bonds form. This is how nylon and polyester are created, as amines react with carboxylic acids or alcohols with acids, linking into long chains. Both processes illustrate the same principle: repetition creates strength and scale. By adding unit after unit, molecules grow from small, mobile species into materials with entirely new properties. The properties of polymers depend not only on the identity of the monomers but also on the way the chains are organized. Linear polymers, with chains lying side by side, can pack tightly and form crystalline regions, making them strong and rigid. Branched polymers, with side chains sticking out, pack less tightly and remain flexible. Cross-linked polymers, where chains are connected by covalent bonds, become networks with high strength and durability. Vulcanized rubber, created by adding sulfur cross-links to natural rubber, is an example that revolutionized industry, making rubber stronger and more resistant to temperature changes. This structural control reveals how polymers, though built from simple repeating units, offer nearly endless variety in form and function. Polymers are also central to modern life in ways we often take for granted. The fibers in clothing, the plastics in packaging, the coatings on wires, the components of electronics, all rely on polymer chemistry. In medicine, polymers are used in sutures, implants, and controlled-release drug delivery systems. In technology, conductive polymers are opening new possibilities for flexible electronics and lightweight batteries. Even in space exploration, polymers form the materials that protect astronauts and equipment in extreme environments. The reach of polymers extends across every part of society, showing how organic chemistry continues to shape our material world. At the same time, polymers remind us of challenges. Many synthetic polymers, particularly plastics, are not biodegradable and accumulate in the environment. Plastic pollution in oceans, soils, and food chains has become a global concern. This has inspired chemists to design new biodegradable polymers and to revisit natural polymers as sustainable alternatives. Polylactic acid, derived from renewable resources such as cornstarch, is one example of a biodegradable polymer now used in packaging and disposable items. Advances in recycling, green chemistry, and sustainable materials show how the science of polymers is adapting to meet the needs of both humanity and the planet. The story of polymers is also one of contrast. Natural polymers, like proteins and DNA, are precise, information-rich, and biodegradable. Synthetic polymers, like polyethylene and nylon, are durable, versatile, and often resistant to decay. Nature builds polymers with exquisite control over sequence and shape, while humans build polymers with efficiency and scale. The future of materials science lies in combining these approaches, creating synthetic polymers that are as sustainable as natural ones, and natural polymers that can be engineered for new purposes. This balance reflects the continuing dialogue between organic chemistry and the world it serves. As we reflect on polymers and materials, it becomes clear that repetition, structure, and design are central themes. From amino acids forming proteins to ethene molecules forming polyethylene, the principle is the same. Small units joined in long chains produce new properties greater than the sum of their parts. This principle of scaling, of creating strength and diversity through repetition, is a lesson that extends beyond chemistry. It mirrors the way life itself builds complexity from simple elements, the way societies build culture from individual actions, the way music builds harmony from repeated notes. As you let these ideas settle, imagine polymers not as distant or abstract, but as familiar companions. They are in the fibers of the clothes you wear, the walls of the cells in your body, the packaging that protects your food, and the very genetic material that carries your story. Organic chemistry, through polymers, reaches into every corner of existence. In the next stage of our journey, we will turn to the tools used to study these molecules, to spectroscopy and analysis, where light and energy reveal the hidden structures of organic compounds. For now, let the quiet repetition of polymers rest in your mind, a reminder that from the smallest building blocks come the strongest threads of life and material. To truly understand organic chemistry, it is not enough to imagine molecules or draw them on paper. We must also have ways to observe them, to confirm their structures, and to analyze their properties. Spectroscopy and analysis are the tools that allow chemists to peer into the hidden world of molecules. These techniques use light, energy, and matter itself to reveal information that would otherwise remain invisible. They are the eyes and ears of organic chemistry, making it possible to identify unknown compounds, confirm structures, and follow reactions. By approaching these methods calmly, we can see how each one contributes a piece of the puzzle, turning abstract formulas into real, observable facts. One of the simplest yet most powerful techniques is infrared spectroscopy. In this method, molecules are exposed to infrared light, which causes their bonds to vibrate. Different types of bonds absorb light at different frequencies, creating a spectrum that acts like a fingerprint for the molecule. For example, a carbonyl group typically absorbs strongly around 1700 cm to the power of 1, while OH bonds show broad signals near 3200 to 3600 cm to the power of 1. By looking at these patterns, chemists can determine which functional groups are present. Infrared spectroscopy is especially useful for quickly checking whether a molecule contains certain bonds, making it a first step in many analyses. In this way, vibrations, tiny, invisible movements of atoms, become signals that we can detect and interpret. Nuclear magnetic resonance spectroscopy, often called NMR, provides even deeper insight. In NMR, certain nuclei, such as hydrogen or carbon-13, behave like tiny magnets. When placed in a strong magnetic field and exposed to radio waves, these nuclei absorb energy in ways that depend on their chemical environment. The result is a spectrum that shows how many different kinds of hydrogen or carbon atoms are in the molecule and how they are connected. For example, in proton NMR, a signal might show that a hydrogen atom is next to a carbon with an electronegative group, or that multiple hydrogens are arranged symmetrically. Splitting patterns, caused by interactions between neighboring hydrogens, provide further detail about structure. NMR is like listening to the voices of atoms, each speaking with a tone shaped by its surroundings. By carefully interpreting these voices, chemists can reconstruct entire molecular frameworks. Mass spectrometry adds another dimension to analysis. Instead of using light, this technique measures the mass of molecules and their fragments. In mass spectrometry, molecules are ionized and then pass through a magnetic or electric field, where their paths depend on their mass-to-charge ratio. The resulting spectrum shows peaks that correspond to fragments of the molecule. By analyzing these fragments, chemists can determine the molecular weight and often deduce the structure. A parent peak gives the overall mass, while smaller peaks reveal how the molecule breaks apart. Mass spectrometry is incredibly sensitive, able to detect tiny amounts of a substance, and it complements spectroscopy by confirming molecular formulas and revealing fine details. Ultraviolet visible spectroscopy, or UV-Vis, focuses on how molecules absorb light in the ultraviolet and visible regions of the spectrum. Molecules with conjugated systems, where electrons are delocalized across multiple bonds, absorb in these regions. The amount and wavelength of absorption can indicate the presence of aromatic rings, conjugated double bonds, or other features. In practice, UV-vis spectroscopy is often used to study compounds with color, pigments, or molecules involved in light absorption, such as chlorophyll in plants. It connects the molecular world to the visible world, showing how the structures of molecules give rise to the colors we see. Each of these techniques, infrared, NMR, mass spectrometry, and UV-vis, provides different pieces of information. Infrared tells us about functional groups, NMR reveals connectivity and environment, mass spectrometry gives molecular weight and fragmentation patterns, and UV-vis highlights conjugation and light absorption. Together, they create a comprehensive picture. When combined, they allow chemists to identify even complex molecules with confidence. This is why spectroscopy and analysis are so central to organic chemistry. They are not optional extras but essential tools that transform theory into practice. Spectroscopy also connects directly to real-world applications. In medicine, NMR forms the basis of magnetic resonance imaging, or MI, which allows doctors to see inside the human body without invasive procedures. In environmental science, mass spectrometry detects trace pollutants in air, water, and soil. In food chemistry, infrared spectroscopy checks the quality and composition of ingredients. These examples show that the techniques used to study molecules in a laboratory extend outward to benefit society in countless ways. The invisible signals of atoms and bonds become practical tools for health, safety, and technology. It is worth noticing the contrasts among these methods. Infrared focuses on vibrations, while NMR listens to magnetic voices. Mass spectrometry shatters molecules into fragments, while UV-vis observes their interaction with light. Each technique approaches the same goal, understanding molecules from a different angle. Together, they balance one another, filling in gaps and confirming conclusions. By appreciating these contrasts, we avoid the trap of thinking any one technique is complete on its own. Like perspectives in art or viewpoints in philosophy, each adds something unique, and together they create a fuller picture. As you let these ideas settle, imagine the quiet precision of these tools. Molecules are too small to see, yet by using light, magnetism, and energy, chemists have found ways to listen to their vibrations, to detect their fragments, to map their structures. Spectroscopy is like holding a magnifying glass to the invisible, revealing hidden details in patterns and signals. It turns the abstract world of organic chemistry into something concrete and observable. By knowing how to interpret these patterns, we connect imagination with reality. As our journey continues, we will move from understanding molecules through analysis to exploring how they are applied in medicine, where organic chemistry directly shapes the design of drugs and treatments. For now, rest in the calm awareness that even the smallest vibrations, the faintest signals, can reveal great truths. The science of spectroscopy teaches us that within every molecule lies a story, waiting patiently to be heard.
Organic chemistry finds one of its most profound expressions in the field of medicine. Every pill, every treatment, every compound designed to ease pain or cure disease is rooted in the careful manipulation of organic molecules. Medicine is not only about biology but also about chemistry, because the body itself is a complex chemical system. By designing molecules that can interact with this system in precise ways, chemists have created tools that extend life, reduce suffering, and fight illness. To understand the role of organic chemistry in medicine is to see how the abstract principles of bonds and structures are applied to something deeply human, the quest for healing. The story begins with natural products. For thousands of years, people have relied on plants, fungi, and other organisms for remedies. Willow bark, rich in salicin, was used to reduce pain and fever, and later became the inspiration for aspirin. The opium poppy produced morphine, one of the most powerful pain relievers known. The cinchona tree gave quinine, effective against malaria. These natural compounds are all organic molecules, shaped by evolution for roles in the plants and organisms that produce them. Humans, by observation and experimentation, discovered their effects and turned them into medicine. Organic chemistry then allowed us to isolate, study, and eventually synthesize these molecules, making them more accessible and reliable. As organic chemistry advanced, so too did the ability to design synthetic drugs. Aspirin, derived from salicylic acid, was one of the first examples of modifying a natural compound to improve its effectiveness and reduce side effects. Later, sulfur drugs introduced the concept of antibacterial agents, disrupting the growth of microbes. The discovery of penicillin, produced naturally by fungi, opened the age of antibiotics, and organic chemistry made it possible to refine and produce these compounds on a large scale. Each of these breakthroughs depended on understanding how functional groups and molecular structures interact with biological systems. The knowledge of organic chemistry transformed medicine from herbal remedies to precise chemical therapies. The design of drugs relies heavily on the principle that structure determines function. A drug molecule must fit into its target, often a protein, like a key into a lock. If the shape or functional groups are slightly different, the molecule may not work, or it may cause harmful effects. This is why stereochemistry plays such a vital role in pharmaceuticals. Enantiomers, mirror image molecules, can behave very differently in the body. One enantiomer may provide therapeutic benefit, while its mirror image may be inactive or even toxic. The history of thalidomide, where one enantiomer acted as a sedative while the other caused birth defects, is a sobering example of this truth. Today, chemists pay careful attention to chirality when designing medicines, often producing single enantiomer drugs to ensure safety and effectiveness. Medicinal chemistry also demonstrates the contrast between small changes and large effects. Adding or removing a single functional group can dramatically alter how a molecule behaves. A hydroxyl group might increase solubility, allowing the drug to dissolve in the bloodstream more easily. A methyl group might block a site of metabolism, making the drug last longer in the body. These adjustments, though small at the level of atoms, determine how the drug is absorbed, distributed, metabolized, and excreted. This set of processes, known as pharmacokinetics, reflects the intimate connection between organic chemistry and medicine. Each step in the journey of a drug through the body depends on its chemical structure. Beyond small molecules, organic chemistry also plays a role in larger therapeutic agents. Many modern medicines are built on peptides, proteins, and nucleic acid analogues. These molecules are themselves products of organic chemistry, made of the same carbon-based bonds and functional groups. Advances in synthetic methods allow chemists to design peptide drugs that mimic natural hormones or RNA-based therapies that target genetic diseases. Even vaccines, which often use proteins or nucleic acids to train the immune system, rely on principles of organic chemistry for their design and delivery. In this way, the scope of medicinal chemistry extends beyond traditional small molecules to embrace the larger biomolecules of life. Organic chemistry also helps explain the balance between medicines and poisons. The same principles that allow a molecule to heal can also cause harm if misapplied. Many toxins are organic molecules that interact with biological systems in destructive ways. For example, cyanide disrupts cellular respiration by binding to enzymes, while botulinum toxin, a protein, blocks nerve signals. The difference between a drug and a poison often lies in the dose, the context, and the design of the molecule. This duality reminds us of the responsibility that comes with chemical knowledge, to use it wisely for the benefit of health. Modern drug discovery relies heavily on analysis and design guided by organic chemistry. High-throughput screening, computer modeling, and structure-based design all rest on the understanding of how molecules interact. Chemists can model how a potential drug fits into the active site of an enzyme, predict which functional groups will enhance binding, and synthesize variations to test. Each cycle of design, synthesis, and testing is grounded in the language of organic chemistry. The process is slow, often taking years, but it has produced life-saving medicines for conditions ranging from cancer to heart disease to viral infections. The future of organic chemistry in medicine points toward personalized therapies, green synthesis, and new molecular technologies. Drugs are being designed to match the genetic profile of individuals, increasing effectiveness and reducing side effects. Sustainable chemistry is reducing the environmental impact of drug production, using renewable resources and cleaner methods. New classes of molecules, such as nanomedicines and gene editing tools, are expanding what medicine can achieve. Yet through all these advances, the foundation remains the same: the careful design and manipulation of organic molecules to serve human health. As you let these ideas settle, think of organic chemistry in medicine as a bridge. On one side lies the abstract world of atoms, bonds, and reactions. On the other lies the deeply human world of healing, comfort, and survival. The bridge is built from functional groups, stereochemistry, and molecular design, allowing knowledge to flow from theory into practice. Each capsule of medicine, each drop of liquid therapy, each injection is a quiet testimony to the power of organic chemistry applied to life. By understanding this connection, we see not only how science advances but how it touches our lives in intimate and transformative ways.
When we look toward the future of organic chemistry, we see a field that is both rooted in tradition and constantly evolving. The foundations we have explored, atoms, bonds, functional groups, reactions, and mechanisms, remain the same, yet the ways in which chemists apply them continue to expand into new and unexpected territories. The story of organic chemistry is not static but dynamic, shaped by the needs of society, the challenges of the environment, and the possibilities of technology. As we think calmly about where this science is heading, we find ourselves looking at themes of sustainability, innovation, and integration with other fields. One of the most urgent areas for the future is green chemistry. Traditional chemical processes often rely on toxic solvents, heavy metals, or large amounts of energy, leading to waste and pollution. Green chemistry seeks to design methods that minimize harm, using renewable resources, cleaner reactions, and biodegradable products. For example, catalysts that allow reactions to proceed under mild conditions reduce the need for extreme heat or pressure. Solvent-free reactions or the use of water as a medium offer safer alternatives to volatile organic solvents. The design of biodegradable plastics and environmentally friendly pharmaceuticals shows how organic chemistry can address global problems such as pollution and sustainability. The principle guiding these efforts is that chemistry should not only create but also care for the systems in which it operates. Another frontier is nanotechnology. At the scale of billionths of a meter, molecules can be arranged with precision to create new materials and devices. Organic chemistry provides the building blocks for these nanostructures, from carbon nanotubes to molecular machines. Nanomedicine, for example, uses nanoparticles to deliver drugs directly to diseased cells, reducing side effects and increasing effectiveness. Organic semiconductors are being developed for lightweight, flexible electronics, solar panels, and sensors. These advances show how the creativity of carbon-based chemistry extends into the design of entirely new technologies, blurring the line between chemistry, physics, and engineering. The future of organic chemistry is also deeply tied to medicine and biology. Personalized medicine, tailored to an individual's genetic profile, relies on designing molecules that target specific proteins or pathways. Organic chemists are working on drugs that interact with DNA or RNA, allowing for therapies against genetic diseases. Advances in synthetic biology, where organisms are engineered to produce useful compounds, depend on the ability to manipulate and design organic molecules. Even gene editing tools like CRISPR involve careful design of molecules that can recognize and alter specific sequences of DNA. In these ways, organic chemistry is not only studying life but shaping its possibilities. Another area of growth is materials science. Organic polymers, composites, and smart materials are being designed with properties that change in response to heat, light, or pressure. Self-healing materials that repair themselves when damaged, or responsive surfaces that adjust to environmental conditions, are already being explored. Organic electronics promise devices that are lighter, more flexible, and more sustainable than traditional silicon-based technologies. These innovations suggest a future where organic chemistry shapes not only medicine and biology but also the tools we use in daily life. The contrast between challenges and opportunities is especially clear when thinking about energy. Fossil fuels, long the dominant source of energy, are themselves mixtures of organic molecules. Yet their use has led to climate change and environmental harm. Organic chemistry now plays a role in developing alternatives, from biofuels made of renewable plant matter to organic photovoltaic materials that convert sunlight into electricity. The same principles of bonds, reactions, and structures that once explained combustion are now being used to design sustainable energy solutions. This shift illustrates how organic chemistry adapts, applying old knowledge to new problems with a vision for the future. Education and communication are also part of the future. As the field becomes more complex, the need for clear explanations and accessible learning grows. Digital tools, computer modeling, and even artificial intelligence are becoming part of how chemists design molecules and predict reactions. At the same time, outreach and education help ensure that society understands both the benefits and the responsibilities of organic chemistry. The future will require not only technical advances but also cultural ones, where chemistry is seen not as a mystery but as an essential part of human progress. As we reflect, it is clear that the future of organic chemistry is shaped by balance. On one side lies the challenge of sustainability, ensuring that our chemical practices do not harm the environment. On the other lies the promise of innovation, creating new medicines, materials, and technologies. The balance between these two themes will guide the field forward. Just as molecules find stability by balancing charges and energies, so too must organic chemistry find balance between creation and care, invention and responsibility. Let these thoughts rest gently in your mind, as a vision rather than a demand. The future of organic chemistry is vast, and no single person can grasp it all. But by seeing its directions, green chemistry, nanotechnology, medicine, materials, and energy, we can sense the outlines of what is to come. The molecules of tomorrow are being imagined today, and the principles you have learned form the foundation for all that will be built. Organic chemistry will continue to be the language of life, the architect of materials, and the guide of medicine, always evolving, always expanding. As we come to the end of this long and gentle journey through organic chemistry, it is important to pause, to breathe slowly, and to reflect on what has unfolded. We began with the smallest units of matter, the atoms and bonds that form the foundation of all molecules. Step by step, we moved through functional groups, hydrocarbons, stereochemistry, reactions, and mechanisms. We saw how these ideas expand outward into life processes, into polymers and materials, into the methods of spectroscopy and analysis, and into the field of medicine. Finally, we looked ahead to the future, where organic chemistry continues to shape technology, sustainability, and innovation. By walking calmly through these sections, we have not only learned facts but also followed a rhythm of knowledge that mirrors the steady flow of life itself. At its heart, organic chemistry is the study of carbon, yet in truth it is much more than that. Carbon provides the framework, but what gives meaning is the way it interacts, the way it forms endless variations, the way it becomes the language of living and non-living worlds alike. Through simple bonds and repeating patterns, carbon gives rise to sugars and fats, proteins and DNA, plastics and dyes, medicines and fuels. It is not merely a scientific topic but a reminder that complexity emerges from simplicity, that the richness of life is built from a few basic rules repeated in countless ways. Looking back across the sections, we notice the contrasts that guided us. Stability and reactivity, polar and non-polar, saturated and unsaturated, natural and synthetic, healing and harm. These pairs remind us that chemistry, like life, is full of balance. Molecules exist in tension between forces, and their behavior reflects the harmony they achieve. In this way, organic chemistry is not only a subject to be studied but also a metaphor for understanding. Just as bonds form by sharing electrons, so too does life thrive through cooperation. Just as reactions require balance between energy gained and energy spent, so too do our lives require balance between effort and rest. The applications of organic chemistry bring this perspective into daily experience. Every time we take a breath, glucose fuels our cells. Every time we eat, carbohydrates and lipids sustain us. Every time we heal, medicines designed by chemists intervene in precise ways. The clothes we wear, the materials around us, the energy that powers our world, all are threads woven from organic molecules. To reflect on this is to see that chemistry is not distant or abstract, but present in every moment of life. The lecture may have spoken calmly about structures and reactions, but beneath the calmness is a profound truth. Organic chemistry is life story written in the language of molecules. As we bring the lecture to its close, let us also consider the future once more. The challenges of sustainability, the design of green materials, the development of new medicines, and the exploration of nanotechnology all rest on the same principles we have studied. The future is not separate from the present but grows from it, just as a tree grows from its roots. The knowledge of atoms, bonds, and functional groups is not trivial or outdated, it is the soil in which new discoveries are planted. By remembering this, we carry forward both an appreciation for what has been achieved and a quiet confidence in what is still to come. The journey has also been about rhythm and rest. Learning does not need to be hurried or stressful. Just as molecules find their most stable arrangements by minimizing energy, so too does the mind learn best when calm. Listening to the steady flow of concepts while drifting toward sleep allows knowledge to settle gently, without force. You may not recall every detail consciously, but the patterns and contrasts will remain, shaping your understanding little by little. In this sense, the lecture has been not only about chemistry but also about a way of learning, a way of allowing information to blend with relaxation. Think now of the path we have taken. From the mystery of vitalism to the clarity of modern science. From the abstract idea of bonds to the real-world power of medicines and materials. From the invisible vibrations of molecules to the global challenges of sustainability. The path has been long, but it has also been steady, each step leading naturally to the next. This continuity mirrors the continuity of chemistry itself, where reactions lead to products, and products become new reactants, in an endless chain of transformation. As you rest in this moment, let the weight of information lift, leaving only the calm awareness of connection. Connection between carbon and life, between molecules and medicine, between chemistry and the everyday world. Knowledge is not meant to be a burden but a companion, something to enrich and deepen our experience. Organic chemistry, seen in this way, is not simply a subject to be studied but a way of seeing the world more clearly, with patience and appreciation. With this, our lecture comes to a close. Allow the calm cadence of words to fade into silence, carrying with it both the facts of organic chemistry and the gentle rhythm of rest. May the ideas you have heard settle quietly in your mind, not as rigid memorization but as seeds that may grow over time. You have walked through the landscape of molecules, and now you may let it dissolve into the background, as you drift further into stillness. In the calm balance of science and rest, knowledge and peace, let this journey rest with you, a quiet companion in the night.